In this video, I am going to cover naming ionic compounds. So remember, in an ionic compound, in that ionic bond, it involves the transfer of electrons. So when you have electrons transferred, what you get is the generation of ions. You have negatively charged ions called anions, because they are the things that take the electrons away from the cation, which ends up positively charged. So when you're naming these things, and if you have my packet, this is page 2 in the packet, what you want to do first is figure out the oxidation numbers of the anion. So oxygen, it has 6 valence electrons, so to get its valence shell full of electrons to be more stable, it will tend to gain 2 electrons. So that's why it has a -2 charge. When you are naming these ionic compounds, you have to pay attention to the endings for these. So on this page, they are binary, which means you have just 2 elements in there. You tend to have a metal that ends up being the cation and a non-metal that ends up being the anion. The non-metal, the anion, so the negatively charged ion, the ending for that in a binary ionic compound always ends in IDE. And remember, binary means there's 2 different types of elements in there. So oxygen becomes oxide. Nitrogen becomes nitride. Iodine becomes iodide. And fluorine becomes fluoride. The positively charged ions, the cations, you do not change the endings of those. So they tend to be the metals. You just write their name how it is off the periodic table. So aluminum has a +3 oxidation number, and you just write the name as aluminum. When you are figuring out the formulas, the overall charge for that compound should be neutral. So the positives and the negatives should balance each other out. So when you're working with this one, you have aluminum that's +3, you have chlorine that's -1. And the easiest way to do this is crisscross the oxidation numbers. So that 3, from the +3 for aluminum, you'll write that as a subscript for chlorine. Now chlorine has an oxidation number of -1. So the 1 would go with the aluminum, but you never actually have to write a 1. So what you get is AlCl3. And this is a nice easy way to get those compounds to be electrically neutral. Now I'm going to write a little bit more on this, so don't write this in this box, but if we're talking about AlCl3, the reason why we crisscross those numbers is, imagine this thing kind of split in half. You have the anion on the right hand side, and that's chlorine, and it has a -1 charge. Now there's 3 chlorines, each of which is supplying a -1 charge. So overall, the right hand side of that compound has a total negative charge, or total charge of -3. The aluminum has a +3 oxidation number. There's only 1 aluminum, so you get a total +3. And the reason why we crisscross these oxidation numbers is to get those positives and negatives to balance out. Crisscrossing the oxidation numbers is a nice, quick way of doing that. It balances these things out nice and easy, and it ends up making writing binary ionic compounds pretty straightforward. There are a couple things you have to look for, though, when you're doing this. And I'm going to jump around a little bit to get to different examples. When you have aluminum bonded to the nitrogen here, that becomes nitride. So you have aluminum that's +3, nitrogen that's -3. When you first crisscross those numbers, you probably think Al3N3. Think about those subscripts, these little numbers, almost like if it was a fraction. If you can reduce them, you have to. So you don't want to leave it as Al3N3. You want to change it to Aln, and that ends up being the formula for aluminum nitride. Now, if you're working on a chart like this, don't bother writing the names in each individual boxes. What you see with the example that I have here, the way you get the name is you take the name of the cation, which in this case was barium, and the name of the anion, which is chloride in this case, and you just put them together. You always write the cation first, and you always write the anion second. And get in the habit of doing that, because when we move into chemical equations, it's going to make it much easier if you're very consistent Put the cation first, the anion second. Now another example where you get things crossing out, canceling out, is with barium oxide. Barium's a +2, oxygen's a -2. Now those 2's cancel out, which is why you get BaO. I'm going to erase this and scroll down some. When we are down at the bottom, you see how I have lead written twice. There is a reason for that. Your periodic table in your reference packet, what you want to do is look at this and you find lead. It's atomic number 82, so it's down here. And what you want to do is in the upper right hand corner, there are numbers for that lead. Now it's kind of blurry on this screen, but on your packets it's nice and clear. So what's written in the upper right hand corner for lead is a 4, 2. That's telling you that lead is multivalent. It has 2 different oxidation numbers that it can have. So it could either be +2 or +4. So just saying something like lead oxide is not descriptive enough. You have to say either lead 2 oxide or lead 4 oxide. And a lot of the metals that are in the transition area have multiple oxidation numbers. Like if you see iron, it could be a +2 or +3. Nickel could be +2 or +3. You have chromium, could be a +6, a +3, or a +2. You have a bunch of different ones. So whenever you're working with ionic compounds, always look at the metal first. Look it up on the periodic table. If it does not have any numbers in the upper right hand corner, like if you look at sodium for example, over on the left, atomic number 11, there's no numbers in the upper right hand corner. That's telling you sodium really only forms 1 oxidation number, which is a +1. So it ends up making it a little easier working with sodium than working with something like lead that could be a 4 or a 2. So that's why I wrote it as +4 and +2. And the way you designate it between those is by using a Roman numeral. So I have it as lead 2 or lead 4, and the Roman numeral just refers to the oxidation number. Now you do this the same way we've done the other ones. So say we're talking about lead 2 oxide, which was this column right here. Alright, so you have lead, that's a +2, oxide, that's a -2. Those 2's cancel out, so you might write Pb2O2 at first, but remember, if you can reduce them, those subscripts you have to, so you get PbO. Now the name for this is still the same way we've named it before. You take the cation, which is lead 2, and you combine it with the anion, which is oxide. So the name for that one is just said lead 2 oxide. Now the one directly below that, you have lead, that's a +4, and oxygen, that's a -2. So you crisscross the numbers like we've been doing, Pb2O4, but now you have a 2 and a 4. Think about that as a fraction again. You can reduce that, so you'll get PbO2. And if you were naming this one, it would be lead 4 oxide. All right, I'm going to move on to the next page. Like I said, I'm just going to pick out certain ones here that I think are worth going over. Now on the next page you'll see chromium is listed 3 times because you have 3 different oxidation numbers for chromium, but you end up doing these the same way as we just did on the last page. Remember, these are binary ionic compounds, so they form ions, which means we have to pay attention to their charges. So you get chromium 2, you get chromium 3, and remember we designate those different oxidation numbers using Roman numerals. Oh, I'm putting that in the wrong spot. Hang on a second. So this last one will be chromium 6. And we do these the same way. So this first column here was with bromine. Bromine has a -1 charge, and we change the ending to IDE, so it's bromide. So for this one, you have chromium, that's +2, bonding to bromide, that's -1. You get CrBr2, and you would just say the name as chromium 2 bromide. Just saying chromium bromide is not good enough. So the next one down, you would get CrBr2. Br3. Chromium 3 bromide. And the next one down would be chromium 6 bromide. So you get CrBr6. Make sure you pay attention to the metals if they are multivalent. I'm going to move on a little bit. I want to look at polyatomic ions. There's also polyatomic ions that are in your reference packet, so you get that on the test. So I'll pull that up real quick to show you what it looks like. All right. So this is one chart, and this is actually a little different than the one you have, but the information is mostly the same. But you have these different polyatomic ions. They have more than one element in them. You get a charge that goes with it, and you get the name. So when you're working on these, for example, on this page, these are polyatomic ions. Now, like I said, I know that looks a little different than the polyatomic ion list you have, but it has all the same information on it. So what you want to do is look up SO4. It has a -2 charge, and it is called sulfate. OH is -1, and that is hydroxide. PO4 is -3, and that's phosphate. CO3 is carbonate, and that's -2, and NO3 is nitrate, and that is -1. Now, this first one on the left here, this is an oddball one. It is the only polyatomic ion that we are going to use that has a positive charge. So this is ammonium. Now when you're doing this, you do it the same way we always have. You take those charges and you're going to crisscross them. So this one from the ammonium would end up going with the sulfate. But what you have to pay attention to is the 2 from the sulfate, from this charge here, goes with the ammonium. Now, when you have more than one of a polyatomic ion, you have to use these parentheses here. So you get NH4 in parentheses with a 2 outside, and SO4, and that is ammonium sulfate. Now, for the next one, the +1 and -1 cancel out. So ammonium hydroxide is just NH4OH. The polyatomic ions basically behave as if they were a single element when you're doing these things. So ammonium phosphate is NH4 with a +1 bonded to PO4, that's a -3. So now what you have is that 3 from the phosphate is going to go with the ammonium. The 1 from the ammonium goes with the phosphate, but you don't actually have to show a 1. Now, that's the general idea with this. You treat the polyatomic ions as if they were single elements, but pay attention to the endings. The previous pages where they were binary, they always ended in IDE. So if you only have 2 different types of elements, the anion always ends in IDE no matter what. Now the polyatomic ions, they vary a little bit. They tend to end in ATE. Some will end in ITE. Hydroxide is one of the odd examples. It's the most common odd example that we have. It's a polyatomic ion that ends in IDE. There are a couple other ones like cyanide and azide and things like that. Hydroxide, I think, is probably the one we will use the most. It is a polyatomic ion, but it ends in IDE. Now, when you go to that polyatomic ion chart, you just write the name exactly how it is. You don't change the ending of it. But that is the general idea with these. They're ionic compounds, so we have to look at the charges, and you crisscross the charges to figure out what the subscripts will be in that compound.